The roar of a motorcycle is the sound of change, a story of engines evolving from crude, smoky machines to today's high-tech marvels. At the core of every motorcycle is thermodynamics, the science of turning heat into motion. The engine's job is simple: convert fuel's chemical energy into the force that spins the wheels. But the universe sets strict limits. The laws of thermodynamics decide how much power is made, how much is lost as heat, and why no engine is ever perfectly efficient. Every design, from combustion chamber shape to cooling fins, is a battle with heat. Waste heat is the engine's constant adversary, threatening to warp metal and destroy parts if not controlled. The history of motorcycles is really a history of mastering heat. Even as electric motors replace combustion, thermodynamics still rules. Batteries, controllers, and motors all generate heat that must be managed. The challenge remains: turn energy into motion, and keep the machine from cooking itself. Whether it's combustion or battery chemistry, the laws of thermodynamics endure. To understand modern engines, we start with their humble beginnings: motorized bicycles with primitive, inefficient engines. These early machines ran on the 4-stroke Otto cycle: intake, compression, power, exhaust. But poor carburation, weak materials, and crude cooling meant most fuel energy was wasted as heat or unburnt exhaust. Low efficiency created excess heat, and poor cooling prevented better designs. Early engines struggled to manage heat, limiting power and reliability. Yet, these clumsy first steps set the stage for future breakthroughs. The journey from smoky singles to today's engines is a story of learning to control heat. Thermodynamics was the lesson every engineer had to master. After World War II, the 2-stroke engine revolutionized motorcycling. Lightweight, powerful, and simple. 2-strokes fire every revolution, making them compact and fast, but at a cost: they waste fuel and emit more pollution. Their design lets fresh fuel escape with exhaust, causing inefficiency and blue smoke. 4-strokes, with better fuel use and cleaner operation, dominated larger bikes. The rivalry between 2-strokes and 4-strokes pushed both to new heights. Emissions rules eventually sidelined 2-strokes, but their impact on motorcycle culture remains. The battle was always about harnessing power while managing heat and waste. As 2-strokes faded, engineers chased perfection in 4-stroke engines. Modern 4-strokes use advanced combustion chambers, multi-valve heads, and precise cooling to squeeze more power from every drop of fuel. Liquid cooling and computer modeling allow higher compression and RPMs, unlocking new performance. Turbochargers, like those on the Kawasaki Ninja H2, force more air into the engine for massive power, but add heat that must be controlled. Intercoolers and advanced cooling systems are now essential. Every improvement is a negotiation with thermodynamics. More power means more heat to manage. The quest for speed is really a quest to master heat. Today's superbikes are triumphs of thermal engineering. Electric motorcycles are the biggest shift since the internal combustion engine. Electric motors are over 90% efficient, but thermodynamics still matters. Batteries, motors, and controllers all generate heat. High currents during acceleration or charging can overheat batteries, risking damage or even thermal runaway. Advanced cooling, liquid jackets, phase change materials keeps electric bikes performing at their peak. The limit isn't just power, but how well heat is managed. Whether burning fuel or moving electrons, the challenge is the same: convert energy to motion, control the heat. Thermodynamics remains the heart of every motorcycle, past, present, and future.